All right. Well, good day, everyone. My name is Vince Lecour. I'm the president of the International Society for Geomorphometry. And today we're having our first coffee talk of the year 2026. So, like usual, I'll just give a little intro for those of you who are not familiar with the organization. So, we're a non-commercial, non-governmental association of researchers and experts that encourages the free exchange of knowledge and opinions about various aspects of the processing of digital elevation model. And our goals are to improve the understanding of the properties of the lens surface as analyzed quantitatively from DEMs and from digital or paper maps, to advance the techniques used in lens surface analysis, to foster international collaboration in the quantitative analysis of the lens surface, and to facilitate communication between scientists and students, advertise relevant conferences, and make public domain datasets and scientific papers widely available. So if you want to engage further with our association, we have a conference every 2 years. The next one will be in 2027 in the Netherlands, so you're all welcome to attend. And we also organize different sessions on geomorphometry at various conferences, for example, the EGU, the AGU, and others. For example, there's going to be one in Japan this year where we're going to have a session on geomorphometry. And we're trying to have some social network activities, so Twitter, X, Instagram, YouTube, and so on. And of course, our coffee talks every 2 months. So what are coffee talks? Well, they are public meetings organized virtually between our main conferences every 2 years. And their aim is to discuss, exchange, initiate, train, present, outline topics, or showcase research agendas, papers, and questions. So we're not going to take more than an hour of your time. Usually we have a 15 to 20-minute presentation by our guest speakers, and then it's followed by open conversation, discussion, question. Um, so we really just wanted to be kind of informal, a way to connect with our researchers like today's speaker, Dr. Chris Lucas, and learn about what's new in our field. So without further ado, I'll stop sharing my screen and I'll invite Chris to share his.
Thank you so much. Let me see if I can scale this first hurdle. Let me just. So I must admit, I have a fun feature of my laptop at the moment where specifically PowerPoint seems to like to randomly close. So if that happens and everything goes blank, no one panic. I'll do the panicking for us. Can you see that okay? Okay, hopefully all good.
Yes, all good.
Okay, so brilliant. Thanks. So thank you very much for inviting me to come and talk. And thank you very much for inviting me again to come and talk after I turns out I'm hopeless at time zones and messed up the timing for the last one. But hopefully second time's a charm. So I'm going to talk to you today about FathomDEM. Okay, so brief introduction to myself. So another hands up moment. Geomorphology as a field is something that I'm very new to. So I joined Fathom about a year and a half ago, and my way into Fathom was working on this FathomDEM project, which I'll introduce to you. My background's in physics and via software engineering and data science and machine learning. I've now found myself kind of combining all of my backgrounds into one, and now I'm working on geospatial intelligence here at Fathom, in particular, the introduction of machine learning to a bunch of those processes. So I'll give a really brief introduction to Fathom, and I'm going to kind of go fairly quickly through Fathom and the whole DEM stuff because these slides are quite generic, and I think the probably more interesting stuff is what exactly FathomDEM is and why we chose the set methodology we did. And I'll try and keep it as close to the 20 minutes, although I expect I'll probably go a little bit over, but I hope that's all right. So as a really quick introduction to Fathom, for those of you that aren't aware, so Fathom came out of the University of Bristol, co-founded by two PhD students and their supervisors. And the goal was to do the kind of water risk intelligence that we can do locally, but for the entire planet. And one of the big challenges of that is how you can scale up the kind of modeling we do with the kind of lack of good data that we have around the world. And DEMs being one of the most important inputs to a flood model to actually do this water risk intelligence was one of the main focuses early on in the company. So why do we need global DEMs, or rather, why do we need why do we care about global data for flooding in particular? Well, this was the kind of original wake up call which happened around the time Fathom was founded. So this was the Thailand floods in 2011. So this was hugely disruptive flood event which happened. It caused $47 billion of economic loss, and only 18 billion of which were kind of accounted for by insurance modeling. So this huge amount of unmodeled loss really indicated there was like a widespread failure in the ability to be able to predict this in industry. So that's where Fathom comes in to kind of fill the gap. So we provide everything from global terrain data, which I'll talk about today, all the way through to kind of our bread and butter, which are the flood maps, and then the kind of risk scores you can build on top of that. And we even do catastrophe models where you kind of convert those risks into kind of numerical values, monetary values for industry. I won't labor the point too much, but as we all know, as you can imagine, if you want to do flooding, a DEM is the core most important part at the beginning of the chain for that. You need to know where the ground is in order to accurately simulate where water is going to go. We have this many step process where we go all the way from our terrain map to mapping out river channels, defining kind of climatic extremes, all the way through to the actual hydrodynamics of where the water will go, and then a pipeline to scale this up to do this globally. And of course, why do we care about terrain? Well, kind of pre-existing DEMs tended to be surface models. So I think we'll talk about COPDEM here, so digital surface model, which in this region, for example, this is the Mekong Delta in Vietnam, is a particularly flood-prone area, given it's so low-lying and near the end of a massive river. You can see that we pick up a lot of the kind of vegetation of the region. And so our task really is wanting to remove that and reveal the underlying terrain that we care about. So basically converting a DSM to a DTM. And in terms of like visualizing why that's important, on the far left here, you can see one of the early DTMs, I believe, is FathomDEM. And if we run our flood simulation with this, you can see we get something which is quite far from the kind of golden standard kind of LiDAR on the right-hand side. And then FABDEM, which I'll introduce in a second, was the kind of introduction to kind of bridging the gap between these two processes. So really, the whole point of this whole thing, to really labor the point, is that an accurate DTM is essential to what we do here at Fathom. So to be concrete, and the way I introduce this task to my friends down the pub is essentially find where the ground is everywhere. Okay, so we've got this great DSM, Copernicus DEM, at 30-meter resolution, and it's derived from satellite data. We know this represents the surfaces of vegetation and buildings and other objects in the terrain. So our task is to predict where they are and remove those to reveal the true terrain underneath. And we're going to, in particular, use machine learning to solve this. And this is where I come in. So I want to highlight one specific thing, and I will probably talk a bit more heavily about our uses of machine learning here and why we chose certain methodologies, because that's really kind of my expertise. But one thing I always like to highlight is this consideration which needs to happen, not in terms of just the machine learning project itself, but in terms of the collaboration between subject matter experts and machine learning people like myself. And I think that's highlighted by this excellent paper from Google back in 2021. And everyone loves a catchy title, but this is an excellent title for the paper, which really lays out their kind of whole thesis, which is everyone wants to do the model work and not the data work. And I think when you look at kind of machine learning, typically in the last 5 or 6, 7 years, I remember being quite junior in this back in the day, kind of people would be very excited to talk about their models. You know, they want to talk about the latest and greatest massive model they've built, and can we use a transformer this and a vision whatever that. But really, most of the errors that you get, this concept of cascading errors throughout your modeling process, which you discover kind of towards the end in this model evaluation, model deployment, you know, the thing doesn't work as expected. A lot of these can be headed off by really considered, by putting really heavy consideration on the problem statement at the beginning and the data collection and kind of collation, right? And this is important, especially because things like the problem statement really take considered understanding of the actual application domain. So if I'd come into this myself and tried to solve this problem, we would have we wouldn't been able to build something anywhere near as good if it wasn't for the fact that I was able to collaborate with subject matter experts like my collaborators, Pete and Lawrence, that really understand this problem and understand the data sources. And I think it's a nice example and something that we really embrace here at Fathom is that coming together of people with maybe a machine learning understanding like me with a set of tools that I could use, but then subject matter experts that really truly understand the data and the problem we're trying to solve and kind of coming together to become bigger than the sum of their parts. So with that in mind, I want to go back and talk about FABDEM. So I mentioned before FABDEM, and I'm sure some of you are familiar with it, is our previous global DEM, which was considered best in its class back in 2022. So to understand what we did next, let's understand FABDEM itself. So the way FABDEM worked was it would take 2D data in the form of various predictors, which can describe the landscape and what the kind of content of the land there. And it would attempt to derive corrections that would be applied to a DSM such as COPDEM, which would bring it in line with a LiDAR, which we're kind of treating as our kind of ground truth DTM. And the way they did this was they said, okay, well, let's consider two broad bases of correction. We're going to try correcting forests and we'll try correcting buildings. And they had a random forest regressor model, which is just looking at a single pixel, single point in space, and trying to make these two predictions. So how much would we correct forests if they're there? How much would we correct buildings if they're there? Subtracting them away, and then combining all of these predictions and post-processing them to hopefully reveal some kind of DTM, which was in this case was FABDEM. And this works really well, but there's a kind of issue with this, and this is that kind of breaking down from a 2D set of data into a point-like prediction. Okay, so what we did instead was we took that step further and we introduced the ability to reason in this 2D space, and this is FathomDEM. So FathomDEM, if we really kind of oversimplify it, is essentially FabDEM plus computer vision. Okay, and this was released last year, and yeah, this is the main crux of this talk. So just to be clear, I want to introduce the field of computer vision because this is my background, and really at its core, the simplest thing is computer vision is the process of enabling computers to reason over images, or more broadly, reasoning over 2D data. So regular 2D data on a grid. And deep learning is a particular way in which we can do computer vision, something which really took off in kind of the late 2010s when there was an abundance of very, very well-labeled data sets. For example, ImageNet was one of the early ones. And huge amounts of compute, which would enable the development of these algorithms, which can do all of this kind of advanced reasoning over this 2D data. So you can do everything from classification of data sets to segmentation of self-driving cars, and I think everyone's very familiar with this. So how does this apply to our world? Well, my favorite way to illustrate this is with the classic game that we all play, is it a horse or is it a zebra? Okay, so if I gave you these two images and I said to you, is that a horse or is it a zebra? Give me a binary classification label for each of those images, which tells me the content of the image, okay? You would look at the image, and because we're humans, we use our visual system to consider the context that's happening in that window and assign a binary label. But if I only showed you one pixel on one point in that image, you're losing a lot of information, okay? So it's much, much harder to make a prediction for a specific point than it is to consider the entire region, where we can then make a much more informed decision. So I kind of make this analogy because this is essentially the same as what FathomDEM was doing, FABDEM, where FABDEM was making a prediction for a specific point by considering a specific point. And really what we've done with FathomDEM is extend that with computer vision to consider the entire context of the image. And just because we're a slightly more technical audience here, I want to actually break this down because that's maybe doing a little bit of disservice to FabDEM. If you consider this process, the modeling process of taking some raw data, pre-processing it, modeling it, making some prediction, post-processing, and then an output DEM, FabDEM would be something like this. So it takes 2D spatial data, it pre-processes it in 2D, but ultimately it models it at one point at a time. So the model, while it is pre-processing and pulling in contextual information for that one specific point, it aggregates that data. This is a kind of lossy transformation where suddenly now we're asking it to make a point-like prediction. And then that point-like prediction is gathered with all the other point-like predictions and scaling it back to 2D and hoping that it's managed to make some kind of sensible, smooth correlation. And in fact, that's why we do post-processing to produce our output DEM. With FathomDEM, it's kind of 2D all the way. So How do we do this? Well, we frame the problem as what we call a pixel-wise regression. So essentially what that means is we take in a grid of data, an image of data, if you like, and this would be a small geographic patch of information. And we ask it to make a prediction also in that same grid. Okay, so you can see here the predictors coming in, and this would be the DSM, in our case, it's Copernicus DEM, plus a bunch of other predictors, which were chosen by the experts to kind of say this is what we think is relevant and important for solving this problem. And we'd ask it to make a prediction. Now, technically, we ask our model to make a correction, which we then create a DTM from, but let's just assume it's the DTM for now, just go with me. So as was typical with machine learning, we have some loss function, and that loss function uses LiDAR to evaluate how well our model has done this translation from DSM to DTM. And finally, we do our classic machine learning where we do block propagation and we update the weights of our neural network. And hopefully the idea is through training over a diverse data set, we can create something which is very good at making this translation from DSM to DTM if we give it some additional information. So what does this model actually look like under the hood? So it's a classic UNet. A UNet is very, very good at reasoning over various levels of data, so kind of levels of resolution. It kind of processes the data through these blocks. And these blocks can be kind of any flavor of kind of computer vision based neural network block you like. And we chose a thing called a max VIT. So it's what's called a multi-axis vision transformer. And I'm going to go into a bit of detail about what exactly a vision transformer is and why we used it. But the main thing to take away from here from this UNet is that we are taking in 2D data of a certain region, and we're making a prediction correction map for that region. Okay, so it's 2D input, 2D reasoning, 2D prediction. So once we trained our model, we then do this prediction for all over the world. We do some kind of blending, and this gives us our final DEM, which is FathomDEM. So I mentioned that we're using this thing called a vision transformer. And I thought, given this was a design choice that we made while developing this model, I thought I'd maybe go into a bit of information about what exactly a vision transformer is and why we think it's quite relevant to this task. And to do that, taking a step back, I think we should first talk about what a transformer is. And again, I'm sure a lot of you are familiar with this, but I thought it'd be quite interesting to go over anyway. So a transformer is kind of the underlying technology which is powering all of these kind of large language models you see today. And a transformer really at the heart of it is it's a particular architecture of neural network which is designed specifically to model sequences of data. And the sequences of data it was first designed to work on were sentences, okay? So to illustrate this, let's consider these two sentences. Number one is the animal didn't cross the street because it was too tired. And the second one was the animal didn't cross the street because it was too wide. And the task I want my model to think about and to answer is what is it referring to, okay? Now in traditional natural language processing, one of the methods was this thing called a bag of words. And a bag of words quite simply was take all of the words from your sentence, chuck them all in the bag. It's an unordered set of the data points you have in your sequence, and use that with a neural network to kind of model what's happening so you can ask this task, what is it referring to? Well, if you make a few steps and fast forward a few years, eventually they settled on this approach called attention. And attention is at the heart of the transformer architecture. It's really the thing which is enabling the reasoning over this sequential data. And attention looks a bit more like this. What attention is doing is it's essentially building a map of all of the elements in that data sequence and how important they are to each other. And you can kind of think of this as like saying, if I want to understand a particular word, what other words do I need to pay attention to? Okay, so it's this attention idea is this mechanism which says, okay, if you want to understand this, really look at this other word. So what does that look like for our task? Okay, so if we put in the first word, the first sentence rather, the animal didn't cross the street because it was too tired. You can see that when I query this word it, which is kind of like saying, what is it referring to? It's got a very strong connection to animal. So it's realized here that the animal was the thing that was too tired and therefore it didn't cross the street. Well, how does that change if we use this attention mechanism on the second sentence? Well, now it is pointing to street. So the street was too wide and that's why the animal didn't cross it. And so it turns out this attention mechanism is an incredibly powerful way of reasoning over this kind of sequential data and making sense of it. So an interesting thing to think about then is how do we take this kind of sequential, data points in a sequence kind of modeling and apply it to images, so our regular 2D gridded data, which isn't really a sequence. So let's take this example. Now we're talking about a vision transformer. Let's take this, let's say we have this input tile of some elevation data. And we can see that maybe we've got some, I think this is some coastal region down here, and we've got, I guess, some mountains or something here and some plains near the ocean. Well, the first thing we do is we take this 2D data and we're going to split it up into patches. Okay, so a 3x3 grid, and each of these is a collection of pixels. But for now, let's just focus on the 3x3. And we're going to flatten it out into a long string. Okay, so now we've got this strip of 9 patches of my original image. And I'm going to take a neural network, some kind of straightforward, kind of probably convolutional style neural network, and I'm going to process each of these images. And the model's task here is to convert this 2D small patch of data into what we call an embedding. So an embedding is essentially kind of putting it into the language of the neural network, right? It's essentially a set of numbers or a vector, if you want to think about it mathematically, which defines specifically that data. So it's encoding kind of, this is a higher altitude region, this is a low altitude region, this has got some coast in it towards the bottom, et cetera, et cetera. And now finally, to encode where exactly those things were in my image, so where Z0 was near the top left and Z8 is the bottom right, I'm going to add a predetermined position encoding. So now we've converted all of these patches into some kind of vector or it's actually a set of numbers. And I've added some position encoding so I can say, here are some data points and this is the order they all come in. And now we can throw this into our super powerful transformer architecture. It can do all that attention encoding like it did with the sentences of words. And then we can put that through the transformer and get an even more powerful understanding so that we can then do some final process and make some prediction. And this is essentially, a very coarse version of how a vision transformer works. So that's all well and good, and that's great if you can use it. And I guess, you know, one nice thing is we're using this architecture, which is proven in other domains for being particularly powerful at reasoning over data. So why not use it? But there's one other reason which I believe a vision transformer is particularly important for this task, and that is receptive field. So by receptive field, what I really mean is how far apart in the image, how far afield in the image am I able to pull in information? Okay, so if we think about a typical neural network, which is built up of sequential layers of processing. And if we think about convolutions, where we're kind of looking, we're applying a convolution to maybe a central point of the image, we can say that on the initial convolution, the only information which is pulled in for that central pixel is a very, very tight region around it. And by the time we get to the third block here, we can see that we're starting to grow the field of influence. So how far afield have we managed to pull in information from the surrounding context in order to make the prediction at the center of the image? Now, if we keep doing that all the way up to block 12, we see we've got this still very diffuse but very centralized receptive field. And it's not really that able to pull in information from further afield, from right near the edges of this kind of window of data, until right at the very end when we have this very loose, very light gray impact, but still it's largely centered. Well, vision transformers are different because we do this patchify process and then we apply the attention mechanism. It turns out way, way, way earlier in the neural network, this central block is able to pull in information from the surrounding areas. And what this means is you've got so much more time to process this additional information, and the model is better able to incorporate things happening further afield in the image. So this is why, one of the reasons why vision transformers are particularly powerful, especially when you need to pull in this kind of global information, this global context, in ways which typical convolutional models aren't necessarily as good at. And I was trying to think of a nice kind of slightly more concrete example for this task, why that's important. And I thought about this. So imagine you're driving down this road and you go through a tree tunnel, okay, which we have lots of in the south of England. So say you're driving along this plain and it's a very smooth grassy field and you've got this very simple linear track of tarmac and it disappears into this tree tunnel, into this forest, this really dense canopy. Okay, so we know that the DSM is going to pick up this kind of like smooth field out here, and it's going to pick up the road, and it's probably going to pick up the tops of the trees. And the task of my vision transformer in this moment is to predict how high, excuse me, the canopy height is. Well, if you're not able to reason beyond the kind of central area of this image, you're not able to realize there's this really crucial piece of information hanging around on the outside here, which is that you have this continuous line that if you're able to see both sides and pull in that information, you'll be able to say, well, I see the correction should probably be on the order of how high this tarmac road is. If you're using a convolutional network, it might just see the canopy and have to make some kind of prediction based on slightly more complex, maybe where the signal is a bit lower and it has to maybe have a bit more uncertainty on its prediction. So really, this is all a kind of roundabout way of saying vision transformers enable us to pull in this kind of larger frequency, or higher frequency, further afield information, and pull it in across the receptor field, which I think is particularly useful for this task. So coming back to FathomDEM, I just want to really quickly talk about the data we use. So as we know, LiDAR doesn't exist across the entire world. And so we have managed to pull together this database of thousands of 1-degree training tiles that we could use. But ultimately, we know that we need to be able to make predictions worldwide. Okay. And one of the big challenges of this task is if we just train a model to learn how to do this DSM to DTM translation in the regions we have LiDAR, we'd have a very different distribution of tiles than we would do for the rest of the world. Okay, so one thing we've done is to really, really carefully do that data task. And remember, I talked about the data cascade, the kind of error cascades in machine learning models. We spent a significant amount of time really kind of exhaustively going through our data and ensuring that we would pick a subset of the training tiles we have available that would be as representative of the rest of the world as possible. So maybe if you said the rest of the world contains N% of forests, but our training tiles don't, then we would subsample down the number of forests we have in our training tiles to kind of try and reflect that. The reason being, the machine learning model is only able to learn what it sees, and it's going to fit the kind of distribution of the data that it sees. So if it sees forests is very important, deserts is not very important, that's what it will learn. So we have to make sure we're kind of addressing that balance. So going on to some results then, I've got a couple qualitative examples here. So this is one's in Alabama in the USA and one's in Nouvelle-Aquitaine in France. So on the left-hand side here, I've got the original LiDAR tile. So this is kind of what we're aiming for. And this is the input DSM. So you can see it's picking up a lot of the kind of surface artifacts, probably fields and canopies and buildings, etc. This is what FABDEM did. So this is the kind of point-by-point correction that was made before. And you can see it does a pretty good job at removing a lot of the artifacts, but still a significant number remain compared to the LiDAR. So when we then do the same task with FathomDEM, we see we gain a much better agreement between FathomDEM and LiDAR. And this is very promising, right? It gives us this kind of confidence that we're moving in the right direction and making something which hopefully is not only reducing kind of average errors, but making kind of something which is qualitatively something which is going to be much more robust, particularly for our task of flooding. So in terms of statistical comparisons, and these are all taken from the paper, if we look at kind of all the pixels in our validation set of data, which were a number of held out tiles that the model didn't see during training, we can do this kind of comparison between the mean error. And obviously we're talking here, I showed 3 DEMs here. FathomDEM and FABDEM are the only 2 trying to be a DTM, obviously. So this is kind of an unfair comparison for COPDEM, but it's helpful to see kind of where the model comes from in terms of how much of a shift it makes in these distributions. And you can see that that FathomDEM produces a much kind of tighter bound around 0, which is exactly what we want to see, right? We're kind of shifting a lot of these errors and becoming a lot more consistent than FathomDEM was. And one really nice thing to do is to look at specific DTMs, which were built for specific tasks. So Diluvian DEM and Delta DTM, I believe, were built specifically for coastal regions with processes to kind of like try and target specifically that region. Well, one really nice thing is that FathomDEM hasn't been trained for any specific region. It's if anything, it's trained agnostically across all regions in our training set. We don't treat any particular area any differently. The loss function is generic everywhere. So the fact that this model can outperform DTMs, which are targeted for specific regions, I think is very promising at the kind of transferability of this approach, which is something I really was happy to see. Our analysis covers not only elevation, but we kind of split that elevation in terms of different regions. So much like I did in the previous slide with specifically coastal pixels, I've also split this out in terms of kind of different building types and canopy, slope. And we look at all these kind of different regions, whether they're bare earth or floodplains, which are obviously very important for Fathom. But we also do this same analysis in terms of the error in, for example, roughness metrics and various other geomorphons. So I'd encourage you to have a look at the paper and dig a bit deeper into that if you like. So that was all nice, and we released this paper back in February. But then a very lovely early Christmas present was to come from the recent DEM intercomparison experiment results. And this was fantastic to see. So this benchmark, and I believe some of the authors on the call, so thank you very much for this really interesting work, is kind of comparing all of these different DEMs, and with the caveat that obviously we have a non-commercial license on ours. It was really great to see that FathomDEM does particularly well and gets a big thumbs up. So yeah, very, very happy to see these results, and I think this kind of comparison is excellent to see. So thank you so much. But really, what we care about at Fathom is, selfishly, we're looking at how we can use this DTM for our own task. And I actually think, as a kind of, if I put my machine learning practitioner hat on, this for me is the kind of real proof in the pudding, right? It's like we can make all these statistical comparisons and we can say, oh, it's great, it's got good roughness, or it's particularly good at coastal regions or whatever. But if it's not good at the task we actually care about, which is in our case is flooding, this is really a kind of test of the realism of this problem of this DEM we've produced. Because I think the flooding will kind of unveil a lot of the kind of issues that may be existing in this data. So an example here is if we run our hydraulic model that we have at Fathom using LiDAR as an input. So this is like the local DEM, which we believe to be the ground truth. And I just want you to focus on these two particular regions. So we have this kind of lovely branching pattern in the lower left here, and a really nice intricate detail in the north side here. Well, if we run this same flooding again with FABDEM, we see that, for example, this branching is just completely closed off, right? We for some reason, there is some kind of artifact remaining in the DEM, which is blocking this channel from flooding. Okay, so the water is blocked, and that's obviously unrealistic if we take LiDAR as the ground truth. And the same here, we lose a lot of this kind of detail in the north side, and that's obviously a shame to see. So when we run FathomDEM through that, and thankfully, I was quite relieved, you can see that we recover a lot of this very similar performance that we get with LiDAR. The branching returns, so it's kind of cleared up whatever artifact was existing on this meander. And we get a lot more of the detail and the same kind of magnitudes of flooding that we want to see according to the LiDAR. So this is really great. Another quick example here, this is same thing but happening in reverse. So now we have FEMA flood zone and again LiDAR, so focus on these two regions. If we look at FABDEM's actually introduced flooding. So clearly there was some overcorrection and it was allowing water to propagate where it shouldn't do. Whereas with FathomDEM, we again recover this much more in line with what we expect to see thanks to LiDAR. So to kind of make this more quantitative, we look at the critical success index, which is essentially a kind of combination of binary performance scores. And it's essentially telling us how well are we recovering that flood. It's like a segmentation kind of metric. And a critical success score of between 0.75 and 0.8 is considered strong performance. And what's really great to see is for these three reference floods that we simulated, not only do we see FathomDEM outperforming FABDEM, but actually it's kind of closing the gap between LiDAR. It's coming comparable with the flood performance we get with a purely LiDAR-driven hydraulic simulation. And that's really given us a lot of confidence that now we know that we are approaching the region where, approaching the domain rather, where the DEM is no longer becoming the bottleneck of our approach, and we need to start considering other things as well. So this is really great, especially given that we can now roll this out globally and have confidence that we're going to be doing something reasonably sensible in other regions too. So finally, I just want to say, well, thank you for listening, but that comes in a second. But FathomDEM is available to download. So we have this available on Zenodo. It's up there with, as I mentioned earlier, a non-commercial license because we are a commercial entity. But for non-commercial users, it's free to use, and we love that people have been using it. Have some great feedback so far. So please follow the QR link, jump on there and download it, and we'd love to hear some feedback. So that just remains to say, in summary, I've introduced some of the machine learning here behind the FathomDEM approach and the model that we've implemented. And we think it's kind of really transforming the terrain data processing that we're doing here at Fathom, and we're really happy to be able to share this with the world. It's yielding another step forward in our global flood modeling capabilities and really helping us advance the products which come downstream from that. And the really exciting thing, I think, is that the model gap between what we're able to do locally, particularly with flooding, and globally is closing, and that's a very exciting time. So with that note, I'd just like to say thank you very much for listening, and I'd love to take any questions.
Thank you so much, Chris. This was fantastic. So we have a good 20 minutes for discussion questions. If you want to raise your hand, you can do it, or write your questions in the chat too, and I can read them. So we have first David, please.
Okay, so thanks for the wonderful talk. And my question relates to the LiDAR training. I guess, do you use LiDAR from a point cloud or from a DEM derived from the point cloud? And then the sort of follow on is, what's the filtering for bare earth that is in the LiDAR training data?
I believe our LiDAR dataset comes from a combination of the two. It's something that we've covered. Unfortunately, I'm not the expert on that particular thing, but I can pass on that question. I think it's a combination of a DEM derived from point cloud data and point cloud data, and the bare earth. Again, I think that was taken from a data set of land cover types. But I believe it's in the paper. But if not, I'm happy to take that out and ask the relevant authors.
Okay, I'll have to check out the paper next.
Sorry about that.
Yeah, I guess the reason it matters, if you're training against data that's not bare earth, then you sort of training against stuff with errors in it. Yeah.
Yeah.
Thank you, David, for your question. We have one in the chat. What is the grid spacing of FathomDEM? Is COP30 the input at 1 arc second / 30 meters?
Yes. Yeah, it's all at 30 meters. Yeah. Yeah.
We have another question. Don't be shy. All right, we got a couple that just came in the chat. So great talk. My curious question is, how about to apply the VIT trained with FAB/COPDEM to other global DEMs such as SRTM-DM?
Yeah, that'd actually be really interesting to try that. I always think so. It's definitely a broad generalization to say that we've learned to translate any DSM to a DTM. We definitely haven't done that, and we've specifically, we'll have learned the intricacies of Copernicus DEM, and particularly the signal that's present in there and how to translate that signal to LiDAR. So it would be very interesting to understand. I'm not familiar with the kind of differences in terms of the ways in which those two, like COPDEM and SRTM, were collected. But I think presumably if they were similar enough, you may find some kind of shared signal that it would be able to interpret. But I'd definitely be interested to have a look at that. Yeah. It's kind of I think it's often this fallacy of machine learning that a lot of people will often try and make out that these things are learning these beautiful generic tasks and they're learning the underlying physics and things, but really you have to think in terms of the task you're given it is the thing it's learned, and if it's learned anything else, that's a positive, right? This idea that emergence comes out of machine learning is often a little bit of a red herring, but I think that'd be a really interesting test to see for sure.
Thank you. Chin, did you have a follow-up on your questions? I saw you turn on your camera, but is that good?
Just thank you. Sorry for my throat is not very good. Thank you.
Sounds good. Thanks. Okay, next question in the chat. We have a comment, an exceptionally fine piece of work. I note that the training and validation datasets, HRDTM, are predominantly distributed across developed countries and regions. How does the FathomDEM output perform in area distant from HRDTM coverage, for instance, in Asia and Africa? The paper mentions its accuracy falls short of FABDEM.
Yeah, so you're always going to be constrained by the quality kind of training data you have. And I think, as expected, we're, like we said, the validation we did was with those LiDAR training tiles. And any validation outside of that, for example, in Africa and Asia, kind of almost by definition is going to fall short of that. However, I believe the model does transform quite well, partly because we've really taken care to kind of select out as representative a set of LiDAR tiles as possible. But yeah, I think when we did the HRDTM assessment, we did see some, like a slight drop in performance in those regions, yeah.
Thank you. Just before I go to Carlos and Hannes, there's one last question in the chat. Is there any possibility that the licensing of the FathomDEM, which is currently share-alike non-commercial, changes in the future for a less restrictive type license?
I think it's probably quite unlikely. Yeah, we try and be as open and publishing all of our work and the methodologies and even giving away the data. But I think for non-commercial, I think that's probably as far as my bosses were allowed to go, because we have to make money at the end of the day.
Sounds good. Thanks. Carlos.
Yeah, thanks, Vince. Chris, thank you so much for this talk. It was really great. I mean, not just the learning the intricacies of FathomDEM, but also that background you gave on machine learning was really good, and the attention and transformers. It was really, I was just thinking on using them for my classes, but going to FathomDEM, I was just thinking on how much of a bottleneck for you guys is the 1 degree tiles that you use for training and validation. Because, just thinking on my reality here in Brazil, we're seeing more and more LiDAR data becoming available, but not for large areas. So maybe if you were able to use smaller tiles, then you would be able to get more and more areas. Like most of the capitals here in Brazil have LiDAR, so you would have a different set of urban scenarios, and even for the tropical rainforests, which are completely different from the forests in the northern hemisphere. Even here in Brazil, Amazon is completely different from the Atlantic forest. So, and we're starting to get those patches of LiDAR. So if you were able to use smaller tiles, you would be able to use those data sets.
Yeah, so thanks for the question and for the lovely comments. So 30 meters was chosen mostly as a kind of because the input to our flood models are at that resolution. And of course, it's possible to go to higher resolutions. I guess the two considerations are, well, abundance of data, so making sure that you can get representative data at that high resolution. The kind of what the model has to learn, like as soon as you zoom into a finer resolution, there's going to be more intricacies that the model's going to have to understand and process and be able to predict. So that's an interesting consideration too. But then ultimately also the just the kind of mechanical throughput of passing that much data through, the model sizes the data sizes start to increase as well. But yeah, I would say that going to a higher resolution is a fairly obvious next step, and it would be great to be able to take advantage of some of these much more high resolution regions, high resolution LiDAR data sets, yeah.
Thank you. Hannes?
Yep. I'm going along the lines about the license. Sorry, maybe you cannot answer on that one, but The uptake of this DM is now mostly, I think, in the commercial world. How do you see this non-commercial license for public administrations if they wanted to use it? Because this is where we could see it, the uptake much more. And then the second question is also, you already mentioned that the DM will not change the license. Are you considering to publish the models for everyone to reuse? Because you mentioned just SRTM, reapply it. So like we have seen it from ChatGPT or whatever, the machine learning models, we see more and more open source models appearing there. Are you considering publishing this kind of models as well before someone needs to redo the work which you have done?
So with regards to the license, yeah, I think it's probably a bit above my pay grade to make any promises there. I think for public institutes, I mean, would that come under a non-commercial? I'm not entirely sure, but I think with respect to the model weights, it's an interesting question. I think all of the data sets we use as inputs are freely available on non-commercial licenses themselves. So there's a potential. I mean, it's something I've made a note, and I can I'm happy to follow up afterwards with if there's something people are interested in. Especially, I think just answering that question now, which is going to play on my mind of how well it would work with something like SRTM. So yeah. It's a good point, and yeah, I'll discuss it with the relevant people.
Okay, thank you. And by the way, I forgot, really interesting presentation. Really.
Oh, thank you.
Yeah.
All right. In the interest of time, we'll take Martin's questions and also the ones that are already in the chat. But I think after that, we'll conclude. So Martin, you can go.
Thanks, Chris, for the nice work and nice presentation. Maybe related to license, although I fully understand that. Can you comment on the investment you guys did in terms of number of GPUs or training time?
Yeah, I'm glad this asked, because it's one of my favorite things. Is basically when I joined because one of the co-founders, Chris Sampson, was basically just said, "Do you reckon you could have a go?" And I was like, "Yeah, cool. How many GPUs have you got?" And he said, "Well, we've got one 1080 Ti GPU and a desktop computer sitting in the corner of the office." And I was like, "Okay, great. Let's see what we can do." So really, okay, we did eventually scale up to use some cloud compute, but I would say, the nice thing about this kind of task is it's very specific, and it's over a very specific. It's a very specific task, whereas the kind of gigantic compute you see in like these foundation models are trying to do a billion things at once, right? So because we have this very well-defined task and we can make certain optimizations to allow us to kind of be very targeted, we really, I would say, used a minimal amount of compute especially compared to what you see in the kind of foundation land. So yeah, again, I think it was listed in the paper, but from memory, I don't think we used anything more powerful than maybe L40S or something, which is like, yeah, not super expensive in the cloud for maybe, I think each model took about 10 hours to train or something like that. So again, it's nowhere near the breaking the bank kind of amounts we see from kind of AI these days. So.
Fair enough. Okay, thanks.
Thank you. So we'll go in the chat now. We have a questions on, so could you comment on how it performs along coastlines and whether it can be used to improve coastline definitions?
Sure, yeah, thanks for the question. So as I mentioned, I'm not showing anymore, but in the slides and in the paper, we kind of do a specific breakdown of pixels. We kind of do our traditional kind of metrics like mean error, RMSE, things like that, but just for regions near the coast, and we see really nice performance there. So the performance doesn't drop off particularly as you go near these coastal regions. So yeah, I mean, for example, we do coastal modeling in FATHOM, and we're hoping that we'll introduce this DEM to help with that. Although often at coastal regions you kind of need more resolution than 30 meters, but yeah, if you have a look in the paper, there's some nice description in the supplementary material about specifically coastal regions.
Thank you. Next question is about So we talked about that earlier, about the lack of training points in some places. This example here is about the Amazon watershed. So the question is, did you guys assess how the model generalized to those areas? Because it's common to have reverse discharge process in the Amazon River, intrusion of ocean water into the river, and this is an example of how it's difficult to model terrain on such complex areas.
Yeah, and yeah, as we mentioned before, because we don't have training tiles in that region and validation tiles in that region, we would use different data sets. So I think the HR DTM I think was used. I can't quite remember now, unfortunately. We don't expect to be as good performance there, but the indications we get from looking at the tiles we have that can be as similar to those regions as possible. Obviously, in unique habitats like that, it's not possible, but we see reasonable performance. And yes, ideally we would be able to do this kind of targeted analysis at every single place, as long as we can have the high quality data. It's obviously difficult when you're creating a global DEM, but yeah.
Thank you. Next question from David. What happens at the edge of tiles? Is overlap considered, or are there tile edge effects in the results?
Yeah, so vision transformers are slightly less impacted by edge effects, but they're always impacted by edge effects. I think anyone that tells you otherwise is doing something I don't know about, which is very possible. So what we do is when we make our predictions, we kind of do that final blending. We actually make predictions which overlap between the tiles, and then we have a blending which happens between the two so that we can make our final predictions. So yeah, we account for the fact that predictions, if we make our gridded predictions near the edge are going to be, we expect more uncertain than those in the middle.
Thank you. And the last question. If Fathom with single height per position equals LiDAR performance on floods, does that not mean that the LiDAR is not using point cloud, or are both using land cover info as well? Point cloud might distinguish permeability of vegetation.
Yeah, when we do our flood modeling, I think that's respect to, we are using a DEM derived from LiDAR, I'm pretty sure. So we have like a single value per blip. I don't think the inputs to our hydraulic models are point clouds. So I hope that answers that question.
Sounds good, thank you. I mean, we could have time for one last question if somebody has a burning question that they want to ask before we come. Martin.
Well, if there's time, I think what I remember from the paper and also from the FABDEM paper is that the output is quite noisy, and you have basically a second model doing the noise reduction. Is this something did you basically train not long enough that you could basically reduce that noise further, or how do you see that?
So I think the second model in the paper, yeah. So we basically make our first set of predictions, and in the original FABDEM, there's a kind of reasonable amount of classical computer vision approaches like edge detection and things like that, which help post-process that into something which is continuous, or as reasonably continuous as you would expect from a DEM. For FathomDEM, we do have this second model, which is essentially the same structure, but its task is subtly different, right? It's basically saying, make this thing which we hope is like LiDAR a bit more like LiDAR. So it is kind of it's a much simpler task, and we could use I think we used a much smaller model because it didn't need quite so much horsepower to do that task. But yeah, it is a kind of, I would say, something which could be improved in the future, is a way to encourage the model to be even more kind of consistent with its outputs. And sometimes, when you're looking at regression over a 224 by 224 grid, while it is a lot more kind of consistent with its predictions, and we do have, our loss function, which we're kind of using to guide the model, isn't just mean squared error. It's also considering things like the gradient shift across the image and things like that to try and encourage it to consider the terrain that is in that LiDAR and make it as like that as possible. I think we could potentially have stronger bounds on that, or maybe even a different modeling paradigm. And there's a few that we're kind of thinking about, rather than just regression, which would help give that realism, which regression models typically fall down on.
So then you're working on a second version.
I would like to, yes.
Good.
All right.
But wouldn't we all, as good scientists?
Yeah.
All right. Thank you all for your questions. Thanks so much, Chris, for this fantastic talk. I think it was really interesting. We got a lot of questions. Please reach out to Chris if you have any other questions. Read the paper. We'll see you in 2 months for another coffee talk. But before I let you go, I wanted to reshare the announcement that there's going to be a special session on geomorphometry at the Asia Oceania Geosciences Society meeting in Japan. And so the conference will be held in August, but the abstract deadline is actually this week on January 23rd. So consider submitting an abstract if you can make it. You're going to be able to meet some other colleagues here from the International Society for Geomorphometry. So that's it for today. Thanks again for being there, and we'll see you next time.
Thank you, everyone.